I think there are a few feedback I got from the banquet dinner and other times. Somebody talked about that why the basics have not started earlier than the RFIC. It's a little bit tough. So my approach is little different. That you first face the challenge, then you will feel what is the gap. Then you brush up those gaps in the basic course. So that's why first lecture, the first day lecture was RFIC design. And while I talking about various topics, you might have found that there are something where you need something like a brush up. So immediately in the next half when Mrigang came and he has given you the basics. So maybe now you have a better understanding of the circuits. And today I will try to cover primarily the two units, mixer and power amplifier. Those are the main building blocks of a RF transceiver design. But again, I found from the various discussions, you are all very much interested on the layout, because the layout is very, very critical in both in analog, mixed signal and RF design. Essentially, for any standard process like standard CMOS 180 nanometer process or 65 nanometer process, where the layout is very, very critical. So there are issues like, for example, schematic. After schematic, you make some simulation and get some results. Then you are verifying with your analytically found approach, because you have a pen and paper design first based on the formulas and your initial guess. You arrive into some performance, but then you simulate it and see something. And then you go for further tuning of the circuits, and finally you arrive that, yeah, all these properties or the performance metrics have been achieved. The next phase would be to layout. Once you made the layout, the most critical thing is called the post-layout simulations. So once you do the post-layout simulation, you will find also there is a gap from your desired objective parameters and the post-layout simulated results. Look at the layout, then again go to schematics. This way, few more iterations will finally achieve a post-layout simulation data or the results, which are very much commensurate with your expected results. Then you go for the GDS2 and submit the chip to the fab. So I feel today we will give you some kind of a feeling that you should have the knowledge of the schematics and the simulations, and then you finally go into the layout and then look at the layout, how it differs from the schematic to the layout, and then what are the tricks to be made to make the layout, post-layout simulations within your expected values. Another important aspect is called the process simulators, because you know your temperature may be from -10 to plus 770 degrees centigrades, and all your process corner simulations is very, very important. All the results which we are showing normally in paper or publications, then we say it is actually the normal condition, okay? But when you have the four corners, then you will find a lot of differences, especially on biasing circuits. So with this, let me go with my first topic, mixer. So mixer is a very interesting block actually. So if you look at the antenna, and your RF filter, your LNA, up to that all the frequency is the same. That means there is no such frequency translation, but only this block where you have a translation of frequency. That is, your frequency is now multiplied with the input RF frequency, and they are giving you omega LO minus omega RF or omega LO plus omega RF. So that block is today's discussion in the first half. Now, if you think what is the fundamentals of mixing, I would say it is multiplications. If you just multiply to sinusoidal, like A sin omega t into B sin omega t or cos omega t in your class level algebra, then you will find if you make omega sin omega t into cos omega t or then they will be multiplied, and you can have the product of this and the difference of this frequency omega t, omega 1 minus omega 2 into omega 1 plus omega t. So, that is the fundamentals, that I want to have a multiplication of two signals, that is the mixing part. Now, how we do multiply in a circuit? That has to be understood carefully. Suppose you have a MOS device and you are giving your RF in here, and this is not the actual circuit, but it is a conceptual one. So, what this RF in will do? You will have a current, and that current, and there will be a particular GM for a given current and given biasing condition and W by L ratios. So, if you make the RF in, for example, 0.6 volt is my threshold voltage, right? And normally RF is pretty low, means it is not that say 1 millivolt peak to peak or 100 microvolt, because it is after the LNA, you are giving a gain of 16 dB. So, typically you are expecting 0.1 like that, 100 microvolt, 200 microvolt like this. So, it will, if you bias it at its say threshold level, then the input signal role is to modulate this GM, right. So, it will modulate the transconductance, that means it will vary the current sinusoidally, or whatever be your input RF, it will try to accord that variations. So, you have been able to modulate the current with the same frequency with your RF in, but I require the multiplications. How do you multiply? Now, if you have another transistor in cascade and you apply some square wave or sinusoidal, depending, I will take both of the cases. What will happen? And it gives, say, you are again giving some sort of a bias along with the AC, and the bias is say 0.3 volt, and the VTH of the transistor is the same as 0.6 volt. So, what will happen? This signal is called the local oscillator, input signal, and the local oscillator input signal, it is under your control because you have rightly known how to design a VCO. So, typically you are giving a swing of say 300 millivolt peak to peak, 400 millivolt peak to peak, or 600 millivolt peak to peak, like that. It is up to you. So, this is no longer a small signal, it is called a large signal, or the transistor will act as a switch. So, if the voltage is above say 300 volt, for example, here 300 volt, that is 0.3 plus this 0.3 already biased, then it will cross the threshold and transistor will be on, and in the negative swing the transistor will be off, clear. So, it will act just like a switch. So, what we have done, that you have a modulating current which is a function of the frequency omega RF, and also a switch to the ground, and this is the VDD, where you are switching is done with the frequency omega LO. Clear? What does it mean? That is, the modulation in the transconductance is now switched, or the current that is modulated is now being on and off. You are making some kind of a switching in that current. So, essentially you have been able to convey the omega LO information to the changing current physically. So, that is the multiplication when two quantities A and B are multiplied. So, both of them are changing each other and giving a resultant. So, you have a transconductance variation based on your RF in, and then the changing current is now being switched by a LO signal. So, you are getting an output which will be a both function of omega RF and omega LO. Then you can easily say that when A sin omega t and another one is A2 cos omega t, they are multiplied, you are getting the bit. That means their difference in the frequency. So, my output will be a product of both, and at the end you will get this product as omega LO minus omega RF or omega LO plus omega RF. Clear? You have understood it, how actually the physics behind it. So, that part, now it is your hand whether I will select this omega LO minus omega RF or omega LO plus omega RF, depending upon what kind of filter I will be using. If you have a low pass filter, then you will be getting omega LO minus omega RF. That means it is called the down conversion. And in a power, when you are actually feeding this from a power amplifier for subsequent transmission as a transmitter, then you have to get the omega LO plus omega RF. That means your omega baseband or IF, that means your up conversion. So, one is down conversion and second one is the up conversion. So, if you look at the transceiver, if you look at the transceiver gain, then only here you have a change in the frequency. So, that is the difference from the conventional approach of designing an amplifier and a mixer. Mixer would have a gain, mixer would have a linearity, mixer would have a noise, but how it defines, it can be defined from the point of its frequency translation is that in case of LNA, your input signal and output signal, both the frequency are the same. But whereas in the mixer, the input signal is RF and the output signal is IF. So, conversion gain, we do not call it a simple gain, we imbibe the number called conversion gain. That means frequency gets converted and also it can give you subsequently some kind of a gain. Clear? So, that is the only difference for the analysis, that it is also giving a gain or attenuation depending upon your design, but also it changes the frequency. This is one. Secondly, this mixer, and this is the LNA. So, when you have this mixer and the LNA together, you can think your antenna will be matched with the impedance of the LNA to ensure maximum power transform to optimize the gain of the amplifier, including its noise figure. Fine. Then also in the mixer, you need the similar kind of matching. That means the LNA, which you have assumed to be terminated with a 50 ohm load in this case, then you assume your mixer is also getting the RF in from a 50 ohm source. That should be your design. You just think the steps. When you are designing an LNA as an individual block, you have assumed your input as 50 ohm impedance coming from the antenna radiation resistance, and output is terminated with a 50 ohm, and you have calculated all your S parameters. Similar paradigm should be there in case of mixer design, as if mixer is getting the signal from a 50 ohm source and your output is terminated with a 50 ohm load, and all your definition should be based on that. But LNA and the mixer, they will be a merged structure. LNA cannot be working alone and mixer cannot work alone in a transceiver chain. In that case, mind it, you require further tuning. Now all your data, all your performance has been finalized or optimized assuming the 50 ohm impedance load terminated. But when they are merged, can you really say it is 50 ohm terminated? Theoretically, what I say that, suppose with 50 ohm terminated, it has got a gain of A1 dB and mixer is A2 dB. So, what are you expecting when they are added, A1 plus A2 dB? That is your expectations, because all my impedance parameters are matched. I am expecting that one. But mind it, you will never get it. Always you find LNA mixer merged structure, the gain will be always less than your predicted one. So, what is the next course is you have to actually match again the impedance, output impedance of your LNA with the input impedance of the mixer, fine tune it to get your expected gain, which will come the superpositions of the two LNA. For example, 16 dB and your mixer is giving you say 2 dB gain. So, you are expecting 18 dB gain. You will never get 18 dB, you will get 10 dB or even 9 dB, something like that. Then you actually, these 50 ohm terminations, now it is you remove that one, remove that and you club this with the LNA output with the mixer, and then have an impedance block or transformation block which will actually match both LNA and the mixing block. So, that is the tricks I am giving. So, always you remember, when you design an LNA, please also consider a mixer. Why? This is the first one is the impedance matching problem. Second problem, LNA output will give you a 2.4 gigahertz, okay, or 5.6 gigahertz, and you do not know about the PIN package or the trace, PCB trace, all those impedance matching parasitics, it will be in trouble. But you must be knowing that when two LNA and the mixer is inside the chip, okay, then all the parasitics is within your known region, within your control regions, because you know what is the CGS, what is my, because all the models are available in the silicon itself, right. So, why not you define your gain in a different way, that let us make the LNA and a mixer two standalone and a merged structure of mixer, because mixer I will get the down converted version in IF band and IF band 100 megahertz. So, that will be much easier to control, less parasitic effects. So, think of it, even I can design a LNA while I am diagonizing the LNA characteristics, I can always down convert it to by a mixer inside the chip itself and get the down converted output, and then I characterize both of them. So, you understand the tricks. So, remember that when you those are working on the LNA, try to design a mixer just for the sake of your measurement clarity and easiness. It will be much easier to characterize an LNA if you have a mixer down converter. Otherwise, you have a mixer outside and you down convert it like that. For example, when you say characterize a high voltage circuits, say 10 kV, 20 kV, you know how they are characterizing, they actually scale it down to 10 volt region and then they analyze the total harmonic distortion and so on. Similar things I am asking you to do in the LNA mixers. So two important points where you will be frustrated. One is the gain just to adding would not always be the same. And second is that you should have a mixer in your plan when you are designing an LNA. Then you will get a much better picture of your LNA performance as well as the mixer. If you are not able to do the mixer design, you should have a mixer outside to characterize the LNA. So that is some of the implementation tricks I should able to percolate. So what I am saying this, the same thing, that it is basically multiplications of the two sinusoidal signals A cos omega 1 t and B cos omega 2 t. So one is essentially is the switching and other one is the modulating. So that is a kind of mixing, and you have the up conversion and the down conversions. So let us try to define the gain. So the gain is, as an amplifier you say only gain, but here we call it conversion gain, as the RMS voltage at IF divided by the RMS voltage at RF. So both the frequency are not the same. And the available power, there are two things, available power and the gain, conversion gain. Now the question comes, conversion gain, while defining this one, when the input impedance and the output impedance are the same, then your conversion gain and the available power will be matched. But if they are not the same, then it will differ. So that is another point to be noted, that how you are defining your conversion gain and available power is there is an asymmetric S11 and S22 parameter. You are not within this, that I say that within 2-3 dB LEDs, then probably your available power would not be the same as predicted from the conversion gain, because the loads are different. So when you say that conversion gain in dB and the power is normally not equal, but when their impedance are the same, then they will have. Then another point is that sometime you are expecting your mixer will give you the output as a current, not as a voltage. Then it is called the transconductance conversion gain. So you require sometime its modulating output will be the current, not the voltage. So this is called the transconductance conversion gain. So that is 20 log phi output in IF. So only difference is here, right? The frequency terms have arrived here, which was unlikely in all other amplifier design and so on. And the linearity, that is the most important part of a mixer design. If you tell me that while mixing, while you are designing a mixer, if you have 3 parameters in hand, one is the linearity, second is the gain, and third one is the spectral pureness and so on, which one you will give the most important parameters? I would say that spectral purity is my first priority rather than the gain of the systems. Why? Because this omega LO minus omega RF I want, but it will also come with all their siblings, their harmonics, their intermodulation products, all kind of subharmonic series of things will come, and that will reduce your fundamentals or the desired output signal amplitudes. So spec purity, how much pure, that the F50 is an essential part. If you make a mixer design and then immediately before you go to your gain conversion, etc., you go to your F50 and find out whether your omega LO minus omega RF is coming as a strong brand or not. If you say it comes with the SCART, you know that we call it SCARTs, then it is not a very good mixer design. And I will show you some tricks how to remove that SCARTs to make fundamentals very stronger and isolated from the other harmonics. I will give you. That means I am talking about the nonlinearity. The nonlinearity part will generate those harmonics, and you need to make those nonlinearity as less as possible so that finally you will get my fundamentals and their difference without those harmonics as much as possible. So it is defined by an 1 dB compression points, which have been discussed in the earlier discussions. So I am just quickly going a review of this. You know that it is the alpha 1 is the input signal at first order, then the second order alpha 2 and the third order alpha x cube, and how it relates with the linear term and how it relates with the cubic term, and finally we got the third order intermodulation levels on IIP3, and with respect to the output referred IIP3 and the input referred IIP3 and so on. Then we got it the second order. This is another point. I have not gone in an amplifier design the third order intercept points. What is the third order intercept points? Is twice omega 2 minus omega 1. But here I am giving you second order intermodulation products at omega 2 minus omega 1, which will be more important in today's technology node, where you want to reduce the hardware count in your chip, and then you like to have a simple low IF or zero IF kind of a transceiver systems. You know that today it is an accepted topology. If you want to design a transmitter, you go for low IF. If you want to design a receiver, just the reverse. If you want to go for a transmitter, you will go for zero IF, and if you want to design a receiver, go for low IF. That's a little bit of thumb rule accepted by all the RF community. Because if you go for super heterodyne kind of a structures, it will give you more hard count. You will have 2 or 3 mixing stages and filters. So when you have this kind of a zero IF or direct conversions, then you have omega 1 minus omega 2. The second order intermodulation products is becoming important. So you cannot avoid that part. So we have defined the IIP2 or OIP2 in case of a mixer design, because today's demand is more towards direct conversion receiver than a super heterodyne kind of a receivers. If you have a super heterodyne kind of a receiver, you don't bother about the second order intermodulation products. So let's start with this consideration. Always, you know, any design should start with some kind of a almost vague but little bit of picture in mind, what you want. So it should give an efficient frequency translation, that means your spectrum purity, low noise figure, and low noise figure 10 to 13 is not that low, but you know that don't unnecessarily go and stretch your design to achieve a very low noise in case of a mixer rather than its linearity. I would say that 10 to 13 dB low noise figure is fine, because in the previous stage you have an LNA of 16 dB. So its contribution will be minimal, because NF2 minus 1 divided by the gain of the LNA, in a fractional noise figure will be added to your system. So therefore, you don't bother about that much of the noise figure, but you bother more about the linearity of the systems. So a moderate conversion gain, even I say that even you go for 1 dB or 0 dB negative, doesn't bother, because gain is not that important for a mixer design. You just improve your spectral purity. The linearity, that is the important parts, more minus 6 dBm at IIP3 third order intercept points and so on. But with this mixer, there are few things are coming at free of cost, but all the free cost things are not good. What is that? That LO, when mixed with the RF, it produces its intermodulation products like omega LO minus omega RF. But you cannot ensure that omega LO might also appear in your IF. That is called LO fit through. The local oscillator frequency will fit through to the IF. That means 2.4 gig for your applications will appear at your IF, which you are expecting to get, say, 100 megahertz. So that is one problem. Yeah. this is, I'll talk about that. I'm just giving you, posing the problem in front of you, then how to solve this problem, I will come one by one. So it is because of the isolations. So isolation is one of the prime design challenge in IF design. That means because there is a frequency translation, mind it theoretically, there is a translation from high frequency domain, I am translating to the low frequency domain. So I should isolate the high frequency components to pass through that mixer to go to the low frequency domain. If it goes to the low frequency, then your purpose is not solved. And one of the basic problem is that that is called LO fit through or LO-IF isolation and so on. And I talked about the IF matching. Low distortions means your harmonic contents and power consumptions and area. Okay. So things are very, very important while you will be designing a mixer. But let's again, in any circuit, you should know the physics first. That what is the physics behind its signal to noise ratios, and how this double sideband and a single sideband scheme is important to understand while you will be simulating that one. And this is all the time baffled you. Look at your publications or the results published in literature, whether they have given a SSB noise signal to noise ratio or DSB signal to noise ratios. Most of the time you will be confused. So let me first show you what is that confusions. Suppose you have an RF in fed to a mixer, and what is that? This is a single sideband, right? Clear? And these are the two tones. It is called image. So what is this problem is that omega LO minus omega RF, so and their intermodulation products, that means to image band, will ride on top of that. So when you do that, if you look at this, I am assuming there is no gain in my mixer. So there will be no such change in the amplitude of my signal band. And the white noise is all pervading. So white noise is traced from minus infinity to plus infinity. So the white noise from the sideband is added here, plus the white noise that is folded from the image band will also be added here. Yes or no? What is the image problem? The two tone, their intermodulating things is riding on your desired band. So what does it mean? Also its noise will also add to that. So essentially your noise, thermal noise becomes doubled. Yes or no? Your thermal noise is own noise plus the image band, that noise will be added on top of that. So your noise signal is doubled, whereas your amplitude is not, the signal is not increased or decreased. So what is that? Your signal to noise ratio for a single sideband is half. That means it is less in 3 dB. Clear? So now you understand. Now in case of double sideband, it would not happen. So if you look at the double sideband, this problem will not happen. Well, because in a double sideband, what is happening? This in a double side means omega RF equal to omega LO, where there is no image. So there is no translation of the image noise riding on the top of your signals. So in case of double sideband, you have signal to noise ratio input referred is 1, where it is 3 dB below that one, because you have an additional noise coming from your single sideband. So single sideband noise and the double sideband noise, if you look at both the cases, there is always difference of 3 dB. So there is a difference of 3 dB from the single sideband to the double sideband. So again I repeat that when you have a double sideband or a single sideband, in your PSS analysis, there is a declaration whether you go for SSB analysis or DSB analysis. When you go for SSB analysis, make sure that your image band noise will be added to your signals. So, you will unnecessarily have a 3 dB less than the predicted one. But when you go for double sideband, then the image noise is not incorporated in this, and you have the whatever signal to noise your input signals are unchanged. So, there is a 3 dB gap in between them. So, noise figure, if you look at that, that is why I say that SSB indicates that the desired signal power S resides at only one side of the LO frequency. As noise N from both the wanted sideband and unwanted image band are adding, then the noise figure becomes 2 into N, and for that switching mixer, the LO signal has all the odd harmonics which are multiplied with the RF input signals. So, in principle, noise at the third and the fifth harmonic of the RF signals also contributed to the noise figure, which is called the noise folding. I will come to the noise folding. Another very important physical concept you should take into account, what is called noise folding. So, I am giving a cartoon. So, first of all, if you look at here, so this is my local oscillator with their harmonics and it is input signal. Then when you have that frequency translations, then each of this noise, so this is my fundamental, so it will go into that. Then LO is the second harmonic, third harmonic, fifth, fourth harmonic, like that. If you look at the VLO, if it is a square wave, then look at here, the LO is all the odd harmonics present. And if you look the translation of that, that is Yn, which is the output of the mixer, you can make that H omega t with x and t, that is the time domain, and then we are shifted to the frequency domain, and from the frequency domain there is a convolution in the frequency domain, and then finally we arrive into the power spectral density. And that noise power is coming from your cadence spectra RF. So, when you talk about the P noise or PSS, then actually you are calculating this, right? And then you are only considering the odd harmonics because you are considering the square wave. Now, there is a tricks which you should know. It is your RF in and it is your local oscillator, fine. And then you are getting a sinusoidal signal of low amplitude. You are also feeding with a sinusoidal signal with large amplitude. You know that you are expecting, I am giving a sinusoidal signal, then odd and even harmonic content should present, right, sinusoidal, or fundamentals should come. I would say that the case will be the same as with the square wave or rectangular wave. Why it is like that? Little same, because when the transistor is on, suppose this is the time when the transistor is on. After that, no matters what will be my input signal. So, you can say it is a trapezoid. So, some kind of this kind of wave is coming into your picture. There is a finite rise time, then it plateaus, and then like that, and finally it will be like that. So, you can see that if it is a square wave or rectangular wave, it will be like this, right? But if you have a local oscillator, it should have a finite rise time and the finite fall time. It is a larger rise and fall time, but it will be like that shape, clear? So, large signal model, in a large signal model, suppose 300, 400, 600 millivolt peak to peak you are having, it will also behave like a switching one with a finite rise and fall time. So, which will be there in your output spectrum. So, what I am saying that I will go for rectangular or square kind of LO, it is a very fast rise. I am expecting all the odd harmonics, but when I change it to the sinusoidal case, I should not expect any harmonics because it is the same frequency omega LO minus omega RF, but still you will get, if you take the DFT, you will get all those harmonics. because actually it is a large signals. So it is actually behave as a trapezoidal kind of thing. So it's basically a rectangular wave with a finite rise and the fall time. So similar kind of harmonics you will get, but at the cost of time, because is a finite rise and fall time will cause it is charging and discharging will have some delay and some distortion you can invite. So there is always little bit of confusions whether you go for a rectangular kind of local oscillators or you will go for the pure sinusoidal, because your VCO, what is the problem? VCO will give you sinusoidal signals. So whether you require a wave shaper to make it square or rectangular before it fed to the mixer, or it will just fed directly to that, this is a question. You are intentionally or intuitively will say that I have less harmonic content, so I will go for the harmonic case. But if you increase the amplitude little higher, then you will not actually get rid of all these harmonics. So harmonic contents will be there, less or more, but it will be there, but at the cost of some delay. Clear? And you also understand this local oscillator, how it modulates at, say, this is my fundamentals and third harmonic, fifth harmonic, and the noise signals get modulated. So each of them are modulating, that is called the frequency gets folded, and contribution of each of them is coming in this way. This is also extended in that way. Suppose this is fundamental. So this is the contributions from the third harmonic. So it is also in that way. So that noise gets added. So it is called interpolations of that. And finally, what will be your output noise figure, or noise output will be like that. Clear? So that is a very important concept in the design, is called frequency folding. What is that? All pervading noise coming into the systems. When you look at the contribution of the noise, when you multiply, because all those noises, there is a contribution of each components corresponding to harmonics is adding together and giving you a definite noise profile. You talked about 1 by f noise, 1 by fn minus 1, that is called 1 by f square, 1 by f cube. How these noises are coming? This is all noises are coming because of concept called frequency folding. You call pink noise. So like that. So I am giving you a very simple concepts that how the noise are actually contributed from all the harmonics, because all are translating back to your desired frequency. So that is, I have already mentioned that when you have this double sideband, then your noise figure becomes 0. That means signal to noise ratio at the output and the input is 1 factor. So this is the red line. So noise figure in double sideband equal to noise figure in SSB minus 3 dB. In the literature, make sure whether the noise figure they have given in DSB or it is given in SSB. Most of the time people mistakes. Clear? Then about the classification of the mixer, there are two kinds of mixer. One is the passive one and other one is the active one. And we will talk about the active one more, where you have two kinds of mixing. One is called a switching type and other is the nonlinear type. And look at here, a single-ended passive mixer. This is a single-ended passive mixer. So this is RF in and the MOS is driven by local oscillators. So what will be my conversion gain? Mind it. This is very simple. Any square wave is this 2 by pi cos omega 0 t. So if you look at here, 2 by pi component, then what will be this one? The conversion gain will be RL divided by RL plus R on into 1 by 5, because 2 by pi into half, that one is coming. So the conversion factor, this is called the conversion factors. Okay, that factor is 1 by pi. Half term is coming because of the A sin omega t into b sin omega t equal to half ab cos omega 1 minus omega 2 by 2 and so on. So you half term is coming 2 by pi, 2 goes, so you are getting 1 by pi. So very simple, a passive mixing will give you a conversion gain of 1 by pi. Okay? And if you look at the noise of that, so I am giving a very simplified way to understand very quickly to get into around the kind of a noise. Then the RS, you have a source which is definitely your RF in, and that will have a thermal noise phi square RS, that is the average of the square voltage, and on resistance, which is the on resistance of these transistors. Then that on resistance will also contribute some kind of a noise, which is called the VR on square, and then average of this. Then you have a switch, and then there is a load resistance. So if you can quickly calculate it, that when the switch is on, okay, when the switch is on, and then actually it will be the RS plus R on. So this series combination parallel with the RL will give you the output noise. But when the switch is off, that means this part is off, then you have only the noise contributor is this RL. So it is 4 kT RL. So if you look at the total, if you just an assumption, you are assuming that the RL is very, very high. So you can say that the contribution of the noise when the switch is on is 4 kT RS plus R on. So what is the ballpark? That what is the noise contributed in the source side, that will be my noise when the switch is on. But when the switch is off, then load resistance are coming into the picture, that is 4 kT RL. So this is switch on and switch off. So total power spectral density will be combination of all RL, RS, R on divided by 2, and this R on is the on resistance of these transistors. Simple model, resistive model, 4 kT RS, 4 kT RL, 4 kT R on. But difference is when the switch is on, when the switch is off. Okay, simple. So that is the passive mixing. It is achieving better linearity, but you know that conversion gain is not that good, and linearity degrades when supply voltage lowers because VGS on resistance varying and so on. So passive mixing is an option, but not so popular, I would say that. You can always try to think passive, but most of the time we will be using an active mixing. So let's go into this. Now I am coming into a very fundamental things which somebody raised about the isolations. So this cartoon, in a active mixing, this isolation is becoming an issue. Because if you look right into the expressions of your switching or the square wave, you have a DC part. Remember, you have a DC components plus cos omega 0 t, cos 3 omega 0 t, all the harmonics. But there is a DC part. You are multiplying how? You are multiplying your RF in and local oscillators. Local oscillator is a square which gives you in the frequency spectrum or the frequency domain a DC components. Yes or no? So when it is multiplied with RF in, what is coming at the IF? Come in, come on. So you should be able to respond this. This is an LNA. My RF goes there, and this is the LO. And the LO having a DC components, you remember this one? I have given you the expression, right? Just go through that. This is a DC component half. So omega RF will be multiplied with that. So mind it. So that will be multiplied with that. So the LO will now go to your IF, yes or no? So that is the speaking we talk about LO IF fit through. Similarly, we have RF LO fit through as well as from RF to IF and so on. So this is the typical problem of a mixers. So isolations from the low frequency domain to the high frequency is a very, very important and critical parameters of any mixer design. Coming to this simple, now the implementation type one by one. I want to design a mixer. Already I have understood that one, I want transconductance modulation and series with a switching circuit. That's the mixing first order things. Let's do it by a MOS device. So if you look at here, definitely you need a tank circuits to resonate at the IF bands and this is the RF in and your I biasing is now controlled. So I am giving you a very simple approach how this is coming into the modulation scheme. Just remember quickly that how to define your VGS. You know that ID equal to mu n Cx, that is beta by 2 VGS minus VT whole square. Now what is VGS? VGS is nothing but, in this case it will be V bias plus this RF in V RF cos omega RF t minus V LO cos omega LO t minus VT, yes or no? VGS minus VT. So get to source voltage. And now if you make this square, so which term will be important for you? This is cos square omega RF t or cos square omega LO t is not of your interest. But your interest is A plus B whole square. So A square is not of your interest because that will introduce twice omega. B square is not of your interest, that will introduce twice omega RF, that is the second harmonics. Cos square omega is equal to something cos 2 omega will come. But your interest is product of A and B. So A plus B whole square, A square plus B square twice AB, that twice AB part is important. So that is the product terms. So whenever this square A minus B whole square is coming, then VRF cos omega RF t and VLO cos omega RF t, there are product terms, is your interest. That will give you my intermodulation or the down or up conversions. So you understand how a square law device can be used as a multiplier. Omega LO minus the square terms, I am getting the product of this, yes or no? So you are simple way of understanding a mixing. But what is the problem here? It has got a high chances of LO will fit through this LO will fit through the output IF, because I told you already that you have the switching and all those DC components would come, and also some parasitic path from there, that is drain to gate. So it will have some parasitic path will go to the output. So all these things will come, plus there is a very big thing coming into the short channel effects, because all your design now going to 180 or say deep submicron technology, where the main problem is this: your square law device will now start working as a linear device. So VGS minus VTH, that whole square formula is no longer valid. It is now becoming VGS minus VT. So that square law device is not working. So you have to be careful about choosing the feature size of your transistors so that it is not going to the saturation or short channel effects, so that essentially your square law is not working. So that's the thing. So don't go into the lower feature size. The short channel effects is becoming an extremely important and sensitive issues, especially when you want to use it as a square law device. Clear? Now coming to the single balanced mixer. So this kind of perennial problem coming because of the fit through. Now you have a differential stage. The same square law device will come. In this case, actually, once this transistor is on, then this transistor is off. When this transistor is on and this one is off. This is the way. So you have this VLO, which is your your local oscillator frequency working in high large signal models, and you have the VRF. Then corresponding to VIF will, when the signal is rising in the RF, and when it is switched on, then it will not allow you, when it try to fall, it will actually try to push it up, and then finally at the end you will get this kind of a profile of output at the IF. So you need to concentrate on this profile that I have cartooned here, that how physically the frequency translation occurred. Two frequency, this is the two frequency, one is the LO and other one is the RF. They are nearby because LO frequency and RF frequency are the same, close to that, except this modulation one. But while they are multiplying or switching in a differential stage, then actually your IF profile you will find in that way. In the switching time, actually the current starts, which is about to fall, will rise up, and then it will give a low frequency output components in this way. So that is the main function physically, this one, and then you will have an IF. So you are finding out an IF cannot be a pure sinusoidals because of this. If a two intermingling, if you look at the switching points, this is the switching points here. So at that point the transition occurs. It tries to go down, but the switching is, again the other cycle starts. Switching means what? If one of them turns on, the current is passing to the transistor M1, but whenever it tries to fall down, the another one starts and then the current pushbacks. So there is a transit, there is a transition time. So if it is like that, you cannot have a pure sinusoidal wave. You can have a distorted kind of a sinusoidal wave. So that's why you got this kind of a distorted sinusoidal signals. So if you take the Fourier expression of that, what you will get? All those harmonics. But I have given a balanced mixer. So differential means all the even harmonic will be cancelled. Yes or no? Then only you have the odd harmonics, 3rd, 5th, 7th and 11th harmonic. So that is called a CMOS single balanced mixer. But what is the main drawback of this is that LO IF fit through. This LO and will fit through this. This is my RF. So that is the problem of LO IF fit through. Because of this square law, you know this problem. And typically the gain of this is very easy to calculate, because it is the main, this is my switching, mind it. This is not going to affect my gain. The gain is mainly here. Here the change in the transconductance. So GM into RL is my gain. So GM into R, this is the gain. Then 2 by pi. You remember 2 by pi I mentioned from the cos omega 0 term. So 2 by pi GM into R is becoming the conversion gain of a CMOS single balance mixer. Clear? So that is the conversion gain. Now coming to the, very quickly I say that what kind of current you are expecting from that. I say that when you are multiplying these two signals, omega RF and omega LO, basically output current will be a function of these functions, where this is 4 by pi sin x, 1/3 sin cube x, 1/5 sin 5x. This is the profile. So I am talking about this function. So mathematically this function can be reduced as the sigma functions, and where the sigma function is 4 by pi like that. So this is the mathematical interpretations of that kind of a profile for your analytical or MATLAB coding. Okay? So that is for your extra informations. But essentially that if you know this omega LO2, and then there is a IDC IRF, because there is a DC components over there, okay, in the IRF. So that will, because it is a biasing current and so on. So that current plus the IRF will add, and then you multiply it and then getting the profile, mathematical expressions to this. So now I am going to the famous double balanced mixer with Gilbert configuration. So essentially the Gilbert configuration is nothing but this. But now we have given pair of transistors, two differential pair. So look at here. Earlier it was M1 and M2. Now M3 and M5 and M4 and M6. So 3 and 5, 3, and you know that the drain of the transistors M3 and M6 are connected, and drain of the transistors, your gate of the transistor, this is the, if you look at the VLO, that local oscillator frequency is feeding this one, this is a differential one. So your gate of the terminal of M4, which is called cross connected. So this M3 and M5 forming a differential pair, M6 and M4, and then finally the current coming out of that are going into a differential pair, they cancel each others and they provide you a cancellation, harmonic cancellation much wisely. That is the Gilbert configurations. Typically, you know that this Gilbert configuration is first started with the BJT model, so exponential current. So they are actually adding the current in both the loops in such a way that you will have ultimately a tan hyperbolic functions. If you look at the book Gray and Mayer, there is a fantastic book on the mixer. If you look at the chapter Gray and Mayer, you will find how it has been analyzed in case of bipolar junction BJT based mixer. Please go through that. Don't go to the mixer Gilbert cell just by this MOS, but go to the BJT side. Very well clarified, very well defined. Then you convert using this expression, which I am giving you this one. This is the, if you go for Gray and Mayer, the BJT analysis, then you study this part. How this square law finally give you the expressions of that. I am coming into that. So when you have the bridge, double bridge, then definitely 2 GM R by pi will be 4 GM per by I. So you have a higher gain with better harmonic content. And at the output, you know that you can use, this is an additional things, how to make a differential to single ended. So you can make use of this, and this is for your implementations. But now coming into this, suppose this is my RF. So remember I am talking about the analysis of that. So RF, this is the switching block. So gain is essentially coming from this RF block. So if you look at here, this M1 and M2 transistors, then the IRF plus 1 is mu n Cox WL by 2, K by 2, VGS 1 minus VT square, and IRF minus like that. So if there is a change in current, say delta IRF, and there is current, say this is one 4 such balance, so ISS will be divided by 2. So ISS divided by 2, and this one is ISS divided by 2 minus delta RF. Then finally you will find that delta IRF, the change in the RF current is K VRF square ISS by this, and this expression will give you the very interesting things, that it is a combination of ISS. ISS is the bias current, and it is the product of VRF square, ISS is the fixed current, and K is also fixed, VRF square. So if you can expand it to a polynomial, I am called polynomial fitting, then delta IRF can be expressed in terms of this polynomial, A1 VRF, A2 VRF square, and A3 VRF cube. Okay? Then I am trying to find out the coefficients of this polynomial from these expressions, and that expression will give me A1 equal to K ISS by 4, K2 terms, so my even harmonic terms is cancelled, so A2 K2 A2 term is going 0, and then A3 equal to this. So remember, if I have the polynomial expression of my function and with that coefficient in terms of the device parameters, okay, then I can find the linearity of this. Then my AIP3, remember, square root of 4 by 3 alpha 1 by alpha 3, I mentioned alpha 2 is not there. So you can find out the IIP3 of this mixer using this coefficients, and then you substitute that of alpha 1 and alpha 3. So it is becoming 4 square root by 2 by 3 VGS minus VT. So if you want to increase AIP3 linearity, mind that about VG. So VGS should be large. That is your important observation. That is the omega RF the VGS you are giving should be large. If it is less, then your IIP3 will be deteriorated. Clear? And if you look at the harmonic content, what is the harmonic content? Here I am assuming third harmonic will give me the highest amplitude. So the third harmonic is delta RF3 and divided by the fundamentals. Then it is becoming A3 by, you are using the same coefficients, you are finding VGS 0 minus VT. Again you say that harmonic distortion will be reduced if VGS 0 is high. Remember, it is in the denominator. So VGS 0 has a very important term, and ARF, that is simple, that is your amplitude of your RF. If it is big, then distortion will be high. It will go into the nonlinear region. Okay, you make it small. So RF is always small because LNA, that is where LNA gain will be matched in such a way it should not go in, it should not go to the nonlinear region of the mixer, and harmonic distortion is high. So VGS and ARF. So that is your prime two parameters needs to be controlled to improve its linearity, because my main interest is the linearity and the harmonic distortions. Has to be very much low. So this is the most important observations as a square law devices. Now coming into this, the Gilbert cell mixers. This is the schematic to this, and Gm by 2 pi. But let me go to the noise. The noise part of this Gilbert double side mixings is basically 8 kT RL 1 plus gamma. And gamma value, again I say, this is a most trivial data. For long channel device is 2 by 3, but for short channels this is 2 to 4, and this is the lower gain GM device. So this is the expressions for that, and you can get that reference from this Abidi Darabi book, RF noise in RF CMOS mixers, simple physical models. So you can go through that to find out the noise contributions of this mixer, but I know that noise contribution 13 to 15 dB is in well accepted one. This is little bit of things which is addition to mixer design. Here we try to analyze that noise contributed because of the switching, because LO essentially is a large signal. So how this switching will introduce the noise into my system. So this is the currents at the output, mixer of the output, and this is the switching, this is the switching one. It is the noise, okay, this is the noise, and this is the input signal in the switch, that is your LO. So if there is a switching in it, then actually it retarded the timing current rise and fall, and that introduces some kind of a noise pulse. Is a periodic noise pulse will come in your current output. That is, if you look at the spectrum, then you will get those current pulse, okay, and that we have been analyzed that could be because of this delay, finite time delay of your switching clock. So either the current will be less or current will, because there is a finite time record to switch on. So that time the current will flow either in positive direction or in negative direction. So that give you a transient current pulse of a very small duration that will be reflected in your frequency domain as a current pulse noise. Okay? So this is a little bit of trajectory from what I am teaching at the moment, is you can get some kind of a switching noise in the mixer design because of this finite time delay in a clock. There is a finite rise and fall time in it. Okay? So now I am coming to the mixer design. So I am giving you that my supply voltage is 1.2 volt using 65 nanometer design. DC current is 600 microampere. Load resistance is 2 kilo ohm. Intermediate frequency is 2 megahertz. It's a very practical design. 2 megahertz means your GSM phone is fine. One channel. One channel is 2 megahertz spacing. Good. And conversion gain is moderate, 10 dB. Local oscillator drive is 0.6. What is local oscillator there? I am taking the RF swing. LO swing is 600 millivolt peak to peak and going to the 65 nanometer node. Please take on. I will take question after this because you learn the design. Okay, couple of questions I can take, one or two. Let them pick. If you have any questions, yeah. Very, very bad. So if the harmonic distortion is, your nonlinearity part is high, that is the third, fifth harmonic will come. If your fundamentals are weakened because of the energy gets distributed to that, after the mixer, what is there? You need a filter. And that filter, and then you get an A to D converter. A to D converter has to work in a linear region. So you can take 12-bit ADC. Look at the 12-bit ADC, then quantization noise is 1 by 2 to the power 12 minus 1. To make it linear region, you need at least 1.2 millivolt kind of things. So if your amplitude is less than that, the ADC will not, then you need an amplifier for this. So it will actually, you have to make an amplifier to compensate that one. But if you can have a good fundamentals, then maybe amplifier can be compromised. So look at here, next part is my A to D converter. So now the design is that what is the quantization, what is the minimum signal required in the A to D converter to work in a linear region. So that will come from the VDD by 2 to the power n minus 1. So look at that, I want to get sure that at least the signal from my mixer would be like that, because after mixer filter, and filter will have attenuations, so your signal strength will be less. So that's why unwanted signal is not an acceptable one, because this harmonic distortion will cause this problem. Try to get your spectral much purer. So if I find time, that subharmonic mixing give much better. When I can show you one just spectrum that I have got only the fundamentals. Rest of things are just vanished. Thing is that I am not going into the omega LO minus omega RF. Is omega LO equal to omega RF, then all this harmonic distortion will come. But your omega LO is much, much lower than omega RF. And if there is some interesting tricks you can maintain, then you don't have those harmonics. So if I find time, I will give you. Even you can make it 900 GSM by 900 megahertz. You start your local oscillator potential with 300 megahertz. Just 300 megahertz. So you need a tripler plus a mixer. So that is a very interesting PhD problem. So you need a mixing plus frequency will be triplicated. Then you know your omega LO is 3 times isolated from your RF. So you are fantastic. Like doubler. You can doubler I have already done. So if you make a doubler, 450 megahertz. That is the input frequency, input LO. So, and that is 900 megahertz. So omega LO minus, if the leaf it is leaked at all, it will be 450 megahertz, far away from your desired band. You understand? If it is 900 megahertz point something, their intermodulation or there will give you the undesired part, harmonics and the, but is far off, you are clear of it. So that is one, you need a mixer along with a frequency doubler or tripler. That is a technique. Clear? Yeah. So look at here, there is some resistance, right? Those who are designing mixer, please concentrate on this design. Whether R will be 1K or 0.8K, that actually defines the performance of this mixer. When I started this mixing design, it takes 3 days just to optimize these two resistance. Why? I am just explaining it like that. If R is high, you will get higher gain. Very good, I am get amplitude. But what is happening? The VGS is becoming less. So I am getting my distortion in the output. My God, so how much time you need? Even 778, I remember in my first design, 778 ohm is my optimum resistance, just these two R1 and R2 for a Gilbert mixers. Small variations of that, if it is 800 ohm, I am getting those harmonics, third, fifth harmonics peeping up. So please be careful about this resistance. These two resistance are culprit for the design. Very careful. Yeah, come on. This is 65, right?
This is 65 nanometer, and this is the bias current, and this.
Quick.
The bias currents and this RF transistor and the local oscillator transistors aspect ratio is calculated according to our next slide, where I will show you that this is a first order model. Then we have changed so many after iterations, and then then we have received.
So you have that M1, M2, M4. So M1, M2, their drains are connected, M3, M4 drains are connected, they are cross connected. Finally, you go to the differential pair, and that is the RF in. So main amplifier gain will be coming from these two stages. Okay, come on. Quick.
First, let us first look about this conversion gain.
Yeah.
So the conversion gate, because the IF band is here is 2 megahertz. And
you go to the theoretical prediction and then go to the schematic. Yeah. So this is frequency in megahertz. That is the conversion
approximately gain. At 2 megahertz.
Yeah.
Approximately 11 dB.
So look at here. My frequency is here is 2.4 gig.
Actually, it is 2.5.
2.5 gigahertz, your RF in, and our IF is as 2 megahertz. So we are getting the gain of roughly 11.22 dB at 2 megahertz. That is my IF band. And what was our expectation?
Between 8 to 15.
8 to 15. So fine. Then, but they are more interested about how you are simulating. What is the setting parameters? Can you just explain little bit of things that when you are designing a mixer, how to set your that tool? Yeah, how to make it? Yeah, you just explained it. So please.
So
make
actually, this is a nonlinear analysis first of all, and it's not like a AC or DC or transient analysis which is being done normally in the SPICE. And this is basically, there are three kind of analysis has to be done for the harmonic balance. Harmonic balance is some kind of nature. It's that it will first predict, because it will ask the user what is the predicted value of the input frequency of the RF or local oscillator. Then it will go for at least some stabilization time. Then it will check whether that is the perfect time period or not. If it is satisfied, then only it will start the harmonic balance technique. Harmonic balance is a non-linear differential simultaneous solver actually. It's a time domain, but it will do the FFT inside. So every time period it will calculate, and then it will do the FFT. For the second time period it will again calculate the FFT. Both two subsequent FFTs results, if not, the difference of the results is not a particular value or some lower the threshold value, so it will keeps on calculating for the FFT, and finally it will settle down of the ultimate frequency band which is being present at the output. So here you have to set, it's a little bit confusing. For example, you have to set that it will run the transient or not. If I tell no, then it will do by its automatic consideration. It will run the transient, but it will not ask for me how much time I have to tell him to wait. For example, I am telling here T stabilization time, it is at 20 nanoseconds. So 20 nanoseconds is sufficient time because it will having a more than 20 cycles to stable. And then of course, then I have to tell that whether it will save the initial transient result or not. Because later point of time I can also check whether that my transient analysis is wrong or right. Secondly, there is two things are there. For example, if you go for a tones, there is two parts are there. One is the names and one is the frequency. But in normal harmonic balance, normal means in this case, in the first order, I will go for the only frequencies. But if I select the names, then there are several channels of the IF and local oscillator mixing up, like omega 1, omega 2, 2 omega 1 minus omega 2, omega 2, omega 2 minus omega 1, it will come. So it is a lost of, it is just a list of things it will automatically make some small table and it will ask me which band you want to select, tell me. So I have to select, like I have to select this, or I can select a set of bands and then I can start telling him that you run. But I will go for the frequencies because this particular harmonic balance I will not calculate any kind of noise or intermodulation product. Achha. Second is that number of harmonics. Number of harmonics generally 5 to 10 is sufficient because we are not going for higher harmonics because there is no actually VCO content in this design. If there is a VCO, physical VCO, then I may have to go for little more harmonics. Oversampling factor is basically generally I have to put 1 because it doesn't contains any kind of sampling switch. Otherwise I have to put the sampling switch and the oversampling factor. Secondly is the frequency divider. Oversampling 1. No, it is suggested 1. ADS might be, but in the cadence it is suggested 1. You can go through the cadence support online and you can declare there and they will suggest it is a 1. So this is frequency divided ratio is 1 because I have not used any kind of frequency divider. So it's a 2.5, it's 2.5. And then I don't have to go for a very accuracy for the transient analysis, so moderate is sufficient. And okay, this all. No, that is the problem. And for harmonic balance analysis, this is actually a AC analysis. This is called harmonic balance AC analysis. It basically AC analysis, but not exactly like a linear AC analysis. In AC analysis, generally what you do? You linearize any nonlinear circuit in a small signal domain, and then you apply whatever the input voltage, like 1 volt, so that you can gain it, or you can get the output as a ratio of the output by input. But this is a nonlinear circuit, so you have to go for a nonlinear AC analysis, which is called harmonic balance AC analysis, because there is a 2 input, 1 output. So you have to give what is actually the RF frequency here, and you want to sweep the RF frequency from some region to some region. Of course, that region should contain the IF band. So here I am just going for the stop band is 3G. It's normal AC analysis, I have to go from 1 kilohertz or 1 hertz to 1 terahertz or something to capture the all bandwidth. Here I have to go for only 2.502, let's say this is my actually RF frequency to 3G, and then number of steps I have to give 20. And here I can select a set of ranges. So of course you can see that 2.502 is my actual RF frequency, and 2 megahertz below that is the second subband, which is actually IF band. It is rated as a -1 because it is a less than 2.5 gigahertz. You can select a lot of, like you can give a multiple subbands. So it will come -1, -2, -3, -4 like this. This is the naming convention. And then I have to go for a harmonic balance noise because I have to calculate, or I have to at least parameterize for the noise figure. So in this case, of course, your sweeping of the noise spectrum, to calculate the noise spectrum or to know about the noise spectrum, you have to sweep or you have to capture the range which will be included by the intermediate frequency band. So that is the IF band. So I don't have to go for a RF switching or RF sweeping, rather I will go for some low frequency to 50 megahertz because I know 2 megahertz is my IF band. And then again I have to select a range of frequency, but I have selected here just like 2.5 gigahertz for the first band. One thing is that this normal HB analysis also will give you the local oscillator to the IF band, what is the rejection. So this will so this is around minus 48 or 50 dB, which is leaking. So it is less, means it should be like this.
So minus 48 dB is quite acceptable one. Anything less than minus 40 dB is fine. That is the, which band it is?
It is the 2.4. That is
2.4. That is the leakage. So what
because this is the local oscillator
this one
frequency.
is what? This is the IF, right?
This is the local oscillator.
Local
frequency.
oscillator.
So local oscillator should not interfere with the IF.
IF, yeah.
So this value is less. This is.
So that is, this is the local, this is IF, right? This one?
No, this is local oscillator.
No, you show the IF first. What is the band?
IF is here. IF is 2 megahertz only.
2 megahertz, yeah. So you make your third harmonics with a local oscillator at least minus 40 dB below the IF. Then come to the conversion again.
This is a conversion gain. Yeah.
Yeah. So you got around 11 dB. And what others you would measure?
And second one and third one will be that nice figure. And then this is
so it is a DSB. So that's what we have gone into the DSB noise figure. So find it. So how much is coming?
minus 14 dB.
So 14 dB is your noise figure. So don't bother about that because you have a LNA gain. So that 14 dB will be a very negligible fraction will be added to your system. Anything else you want to?
Transient we can show. Third order intercept point actually is not running.
It will take time.
It will take time. And secondly, this is a spectrum. I can show spectrum.
So third order intercept time will take time. So maybe in the offline.
You can show the
Next part. Layout I will give you in the next after the T.
Sir, I can show the just 1 minute. Differential IF transient output.
Just show the transient output 1 minute.
Because DFT, if you have the more accuracy, you have to run a long transient. So, no.
Yeah, that spectrum you just show. Yeah, that is the. There is IF.
Yes. Another point. I can run.
Sir, I have one question, sir, regarding polynomial equation.
Yeah, question and all this. Yeah.
Sir,
Yeah,
one
question.
Sir, polynomial equation you have been shown you, right?
I can't follow you.
Polynomial equation.
Yeah.
A1 and A3.
Yeah.
The coefficient value of
Alpha
that
1, alpha 2 and alpha 3. I am going to the third.
third. How do we get that values actually? The
No, fitting.
Fitting.
You can theoretically you find out the expression of that.
Yeah.
Then I have given you what will be the alpha 1 as a
Okay.
function of device geometry and the process. So you calculate that alpha 1 and I give you the value of the linearity part square root of 3 by 4 alpha 1 by alpha 3. So you can find out alpha 1 from that and alpha 3 from this, and from there you can calculate. So both way.
From that I could theoretical value could get it from spec, and I could simulate and look cross
Back and forth. So you can calculate from your device geometry, calculate alpha 1, alpha 3, find out the intercept points. Okay. Then you make IF plot, and from that polynomial fitting you can get the coefficients, see, and finalize that one. So that's why it's a simultaneously you can make the mathematical calculations and the simulations, and then you will converge into this. But I am giving you how to do that.
do you not think we might be something difference will be get it from simulation as well as theoretical, right?
Not much,
Not
because
much.
this one is feature size is not going into very high. So mixing, I'm not going into the short channel effects that much. So no, not much.
Thank you, sir.
Question?
Sir, excuse me, sir.
Who?
Yeah, this side.
Yeah, question.
Sir, when I gone through the literature survey, basically on analog multiplier, the two things I normally observed. The first result they are talking about the linearity error, and the second thing is about THD.
About?
THD, total harmonic distortion.
Yeah, harmonic distortion.
So when they're talking about the linearity error, I don't know they are talking about the minus x plus x, and when they are talking about the total harmonic distortion, they are talking about the AC signal. So linearity error consider in what way? What is the significance of that linearity error?
First of all, if you look at the linearity error, suppose you have a predicted output input characteristics, right? So suppose you are plotting x-axis is your input and plotting output as the y-axis, and you need a predicted path that is depending upon these transfer functions. Now actually your simulators you will find, or your experimentally you will find that there is some deviations from the path. So there is a difference in it, the error incorporated. If it is linearly followed, it will be predicted in that way. If it is nonlinear, after some input signal, then you will find that there is a depression or some changes in it. So that is called the nonlinear phenomena in it. But again, the nonlinear phenomena is coming because of the incorporation of harmonic. And the harmonic components are coming intrinsically because of the devices are nonlinear in nature. Essentially, if you look at any devices, they are not linear because this is exponential. And if it is exponential, that is 1 plus x square factorial to x cube factorial to all this nonlinear part is actually inside your chip, inside your device. It is not outside. So when the input signal, now you are giving a first order approximation. So you are giving 1 plus x. So that is the linearity. All your small signal AC model is based on the first order approximations. But in case of RF design, you are cautioned because the second order and third order components are important because they will produce the harmonics, and those harmonics intermodulation will actually lie on your desired band. Otherwise, we will not consider, we will lose some energy, but if it is not of our interest, but their intermodulation, the bits, those are coming to your desired band. That is why you are so concerned about the second order and third order and fifth order, so on. When you go for the power amplifier, even 11th order distortion has to be taken into account. So that is the overall insight of the linearity issue. That linearity is coming actually from the nonlinear IV characteristics of your MOS devices. Here you have to strike, and I showed you basically the transconductance in the first order is del ID del VGS at VDS constant. But actually if you look at the IV characteristics, you will have the second slope, you will have the third slope that correspond to the first order GM, second order GM and the third order GM. And that GM will introduce the alpha 1, alpha 2 and alpha 3 parameters, which will ultimately reflect into IIP3 or OIP3. Clear? So it is, you have to start from the device angle.
So suppose I have taken some effort to reduce the linearity error, this might be because of some other things. So whether this has any impact on the THD also, means suppose linearity error is improved, so can I think, okay, my THD will also improve?
Suppose you are improving your linearity, okay? That means you are getting your fundamentals and other harmonics. The dB level is, suppose this one I say minus 48 dB. So that is a good, because anything below minus 30 dB is acceptable. So you look at how would you define your harmonic distortion? Is that RF amplitude at the third order divided by the RF amplitude at the desired one. So if that dB difference, actually it is the difference of that. So how you suppress your unwanted one from the desired one is a measure of harmonic distortion. So that way you can make the harmonic distortion. Sometimes we call total harmonic distortion. But if you look at the harmonic distortion, your major components are basically third harmonic. Other terms having these more higher the harmonics, it is getting attenuated. Exponentially it is some function. So it is attenuated like that. So you are mostly concerned with the third harmonic. So it is a misnomer that total harmonic distortion becoming third harmonic distortions. Okay, so that's the main reason for this.
Sir,
Question.
sir, as far as device is concerned,
Yeah.
there is a issue of channel charge injection. You have considered a feedback, but channel charge injection also introduces a DC offset. So, what about this? Is it a concern, point of concern herein, or?
That is actually taken into the model, which will, in the model, we will include the channel charge modulations. So, you should declare that channel charge modulations also. So, let us break for a few minutes and then come back. Question.
Sir, you suggested one increasing the VGS for increasing the linearity. I think there are some other techniques also to increase the
Lot of techniques,
linearity.
I am talking especially on the mixer, but when I talk about the power amplifier, it is entirely different way to improve the linearity.
So which one will be the better? Can you
Depending
suggest
upon
me?
which for a mixer design, VGS should have been a better choice, because other, if you want to change, the other components will be degraded. So, then the spectrum purity and so on. So, if you look at, I say that you can compromise with the gain. Okay, you can compromise with the gain, improve the linearity. One option is that you play with that R, the load resistance. Okay, that is essentially changing your GM. Current is being controlled. So two ways: either you control the current or you control the VGS. Finally reflects into its harmonic contents to this. So if you feel that changing the transconductance by the resistance would have been the better approach, go ahead with that. Otherwise, change the W while. But I say, don't change the W while L ratio once it is design is more or less close to your desired value. Then fine tune with your R.
Sir, I have seen in the literature those two transistors, M1 and M2, those basic transistors. They, when you operate them, they produce the third order intermodulation distortion. Their term is negative. So if you cancel those negative terms, so
Exactly
cancellation,
that part I have shown is called linearization techniques by feed forward and feedback.
Feedback.
So feedback path, you can actually, suppose harmonics coming in one phase. If you can generate a feedback and that is coming in opposite phase, and if you superpose to each other, what will happen? Those harmonics gets cancelled. So that is called frequency harmonic cancellation technique. And this technique is called harmonic reduction. When you are reducing the harmonic intrinsically, there is no feedback. So these are two different: harmonic cancellation and harmonic reduction. This is harmonic reduction. How do you reduce it? Intrinsically, from the device point of view, from the circuit point of view. But here you are getting the fraction of the output and then phase changes and superpose it together so that harmonics gets cancelled. So that is called harmonic cancellation.
Thank you.
Digitally assisted circuit.
That is most important, because pre-distortion, all this, that digitally assisted things should have been the best one in some cases, because if you know the transfer function, what he has said, if you know the transfer function, I said tan hyperbolic functions for an exponential circuit. If you can generate an inverse tan hyperbolic spot output, then you can get the signal, transfer it to its inverse transfer functions, and then feed it to you. So what will happen? It will automatically cancel the test. So that inverse transfer function generations can be done digitally. Because all the polynomials can be done digitally. And then you can, that point, harmonic can be cancelled in the output. So that is called predistortions by using digitally assisted. Okay.